Hey everyone, welcome back to Linear Algebra. This is going to be part B of lecture 21. Where we left off, we had just discussed a theorem for the existence and uniqueness of a matrix of a linear transformation. And we did a handful of examples, three good examples, and increasing complexity to that effect. Okay, so now we want to kind of shift gears here a little. We're still obviously going to be talking about this matrix, this matrix of linear transformation, but we want to kind of look at some of the periphery of this guy. So the next theorem is going to show us how the matrix for linear transformation changes when we alter the basis for the domain and the codomain. Okay, so that's the next theorem. So if I have if I've calculated the matrix of a linear transformation with respect to particular bases, maybe we'll say the standard basis like we just went through, and then I want to switch and create maybe a different basis for the domain and the codomain or the codomain, then how can I change my linear transformation matrix to reflect those new bases? What happens? What's the relationship? So here's the theorem. It's kind of a big one, so you have to bear with me as I struggle to write it all down here. But we'll let V and W be finite dimensional vector spaces with basis B and C respectively. We'll let V and W be finite dimensional vector spaces with ordered bases B and C respectively. Okay, so B is the ordered basis for V, C is the ordered basis for W. And so then we're going to let L be a linear transformation from V to W with A, B, C matrix. Okay, so I've got L as a linear transformation from V to W, and A sub BC is the matrix of the linear transformation. Now, suppose that D and E are other ordered bases for V and W respectively. Okay, all right, so I've got separate, distinct ordered bases D and E. We're going to let P is the transition matrix from B to D. Okay, so remember transition matrix from B to D when we were talking about special bases before in the previous sections. And we're going to let Q be the transition matrix from C to E. Okay, so I've got P, transition matrix from B to D, and I've got Q, transition matrix from C to E. Okay. Then the matrix A sub DE for L in terms of ordered basis D and E, bases D and E, is given by, how does this work? Is given by, well, so if I want to calculate A sub DE, that's equal to Q, right? Q, the transition matrix from C to E, times A sub BC, which I already have, times P inverse. P is, of course, the transition matrix from B to D. Okay. All right, so let's think about this a little bit. As I said, this is a very wordy theorem, so let's see if we can kind of break this down a little bit. So I've got V and W. All right, so over here on V, I start with ordered basis B, and on W, I start with ordered basis C. Now I've got a transition matrix A, B, C that, sorry, this is not transition matrix. This is the matrix of L. Right, this is the matrix of the linear transformation with respect to ordered basis B and C. Right now, separately, I've got D and E, right? And I'm interested in how to calculate A sub DE. How do I get that guy? Okay. Well, there is a transition matrix to go from B to D, and we called that P. And there's a transition matrix to go from C to E, we called that Q. And so these two transition matrices play a role. You can basically apply them to this guy in a particular way to flush out this guy. Okay, and so that's what you see here. So A sub DE is equal to Q times A sub BC times P inverse. Okay. All right, now there's a possibly better way to represent this. So the situation can be kind of summed up like we just did, or another way to look at it, the situation can be summed up as, well, so let's start. I've got V coordinatized in B over here, right? And what I'm interested in is I want to get V, I want to apply L to V and get the coordinatization in C. All right, well, we know the way to do that is through this matrix ABC. Right, this is the matrix for L using B and C. B being the basis for the domain, C being the basis for the codomain, L being the linear transformation. Okay, and so similarly, maybe I've got V coordinatized in with some other basis D, and I want to be able to get to L of V coordinatized in some basis E, right? B being distinct from D, and C being potentially distinct from E. Right, so how do I get there? Well, there would be some matrix for L using D and E instead. So I'd have A, D, E. That's the matrix for L using D and E, right? Remember, we can represent L using whatever bases we want. Okay. Now, what connects these two streams? Right? I've got this stream up here, I got this stream down here. What connects them? Well, that's the transition matrix. So here I've got the transition matrix P. And over here I've got the transition matrix Q. Okay, so that's what connects these guys. Okay, so let's do an example, see how this works. Okay, let's take an example and see how this works. And so let's recall the example from the previous section of the linear transformation P3 to R3. Sorry, this has been the running example for this whole lecture, but part A of the lecture had the specifics of this, right? But here was L. Here's L, and it was given by, remember, if I have L of A3x cubed plus A2x squared plus A1x1 plus A0, that's equal to A0 plus A1, and then 2A2, and then A3 minus A0. Okay, we previously found that ABC was equal to 0, 0, 1, 0, 2, 0, 1, 0, 0, and 1, 0, negative 1. Okay, and we found the transition matrix Q from basis C to E previously as well, at part of the previous example. And we said Q was equal to, I'm kind of digging these out, so negative 6, 16, negative 9, and then negative 2, 5, negative 3, and then 3, negative 9, 5. Now, P inverse, I'll just tell you what it is. Right? P inverse, this is going to be inverse of the transition matrix P that goes from D to E. Right? But you may have to spend a little time figuring out what P is first and then P inverse. But P inverse, it turns out, is 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1. That's a nice looking matrix. Please verify for yourself. Okay, and so what this previous theorem says is that I can find ADE, A sub DE, as Q times the linear transformation matrix I know, which is BC, times P inverse. Now Q is the transition matrix P that converts the basis B to D, to the basis D. P is the inverse of the Q is the transition matrix that transitions from C to E in the codomain, and P inverse is the inverse of the transition matrix that transitions from B to D, right? So you kind of look up at the top here. It shows you what these things are, P and Q. And so I just have to multiply A, B, C on the left by Q, on the right by P inverse. And when I do that, here are the actual numbers, and I'll write them out for you. You can verify and make sure you get these matrices and know where they come from. Negative 6, negative 2, 3, 16, 5, negative 9, and then negative 9, negative 3, 5. That's Q. And then ABC we found before, it's 0, 0, 1, 0, 2, 0, 1, 0, 0, 1, 0, negative 1. And then P inverse is this one, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1. And when you multiply all of those together, what do you get? You get negative 1, 1, negative 1, negative 10, 26, negative 15, negative 15, 41, negative 23, negative 9, 25, negative 14. Okay, so that's what you get when you multiply these together. And of course, if you look back at, in lecture part A of the lecture, you'll see that this is the same matrix that we generated in that previous example. Okay, so I know this is a little bit of a difficult section, and you're not alone in thinking that. This is notoriously a challenging section for students, but I think this is a great handful of examples that you can walk through to make sure you're following the arguments. Okay, now just a few more things that we'll throw out here just to kind of round out this section. And so the first one is the idea, we want to bring out this idea of similar matrices. Right? And similar means lots of different things in mathematics, and just like in other areas, similar has a very distinct meaning for linear algebra. So here's kind of the basic build-up here. So suppose L is a linear operator, okay, on a vector space V. Okay, so I got some vector space V. Then if B is a basis for V, right? If B is a basis for V, then there exists, we know this from what we've just been discussing, there exists some matrix A, B, B, right, This is going to be the matrix of a linear transformation. There exists this matrix of a linear transformation for the linear transformation L, for L, with respect to B, right? Okay. Now, if C is some other basis for B, B is some other basis for V, then there exists ACC for L with respect to C. Okay. So we're going to let P be the transition matrix from B to C. Okay, we're going to let P be the transition matrix from basis B to basis C. Okay, so if this is the case, given this setup, notice, what are we going to notice? Well, ACC is equal to P times ABB times P inverse. Okay, so this matrix ACC, matrix of this linear transformation with respect to basis C, is equal to P times ABB, which is the matrix for this linear this linear transformation with respect to basis B times P inverse. P is just the transition matrix from B to C. Okay, this right here sets up the idea of similarity for matrices. This sets up the idea of similarity. Okay, now here's the definition. Here's how we've defined similarity. So we'll let X and Y be n by n matrices. Okay. Then X is similar to Y if and only if Y equals P times X times P inverse for some P. Non-singular, of course, you can see that right there. N by n, of course, because X and Y are both n by n. So for some non-singular n by n matrix P. Okay, so this is what we mean by similar. So if I have two matrices X and Y, and I'm able to find some non-singular n by n matrix P such that P times X times P inverse is equal to Y, then Y is similar to X. X is similar to Y. Right, now notice that this is obvious. Well, maybe not obvious, but hopefully it's obvious, I guess. But you should be able to see that this relationship is reciprocal, right? So if Y equals Px P inverse, then it's true that X should be equal to P inverse Yp, right? So if Y is similar to X, then X is similar to Y, right? P and P inverse are basically just all that matters here is that these are inverses of one another, which is obviously true here as well. So if X is similar to Y, then Y is similar to X, right? Maybe you don't even need to be told that, but just making sure. Okay, that the two are similar. And so that is what we mean by similar. Okay. One more theorem, and this is one that'll come up later again, but I just want to introduce it here. And that is the fact that matrices that are similar have the same characteristic polynomial. And I won't be proving this, but this will come up later, and we'll talk about this more later on in the course. But I want to throw it out there while this idea of similarity is fresh. So if A and B are similar, then P sub A of x, the characteristic polynomial for matrix A, is equal to the characteristic polynomial of matrix B. May not be obvious why that is true, but it is. It is true. Okay. All right. And so that's where I think I'm going to end it. I think we'll end it there. And that, again, I realize that was a very, very dense section. It's well aware of that as I was going through that. Like, okay, this is going to be a very dense section for people. Do your best with it. Okay, do your best. Now, after this section, the next one it'll be much shorter, but it'll be much more profound. A very, very powerful theorem at the center of linear algebra called the dimension theorem. And I don't think many people escape a lecture on the dimension theorem without going, wow, that's interesting. So hang on to your seats, I guess. All right, we'll end it there, and until next time, take care and work hard on. You may need to rewatch that one a couple of times, pull out some textbooks, look up the matrix of linear transformation in your favorite text, and see if you can make heads or tails of that. I'm sure it's not that bad. But I know that is a tricky section. But until next time, take care, and we will talk to you all again soon.